Okay, there we go. Now I'm recording. So as you can see from these curves, I think you talked about in grade 9, like line of best fit, right? Right, where it's like if you've got a scatter plot full of data, can you draw a line that's gonna hit the like majority of the points that could like represent this? Same thing goes for a curve. You can have a curve of best fit where you're gonna actually just like move your line essentially to like fit the data better. So even with this one, as you can see, I can't put a line through this. If I put a line through that, that's not gonna hit everything. Same thing if I go this way. A line's not really like representative of this data.
You gotta do like a loop-de-loop.
I would agree that a loop-de-loop would probably look good. And I would do something kind of like this. That's kind of going through most of the data. So I would say that that's a curve of best fit. Right? What about B, or the second one here? Would you draw a line or would you draw a curve? Yeah? I think a line, and you could probably draw it through like here. Something like that. So a line would be better because it looks like the data is like constantly going up by the same amount, right? What about the third one? Line or curve? Line. I agree too. Looks like I can maybe draw it something like that. And last one, would you say line or curve? Curve. And again, you can kind of see the shape of the data. It doesn't have to be perfect, but it's like something like that where it's hitting most of the points. So this would be a curve, right? Easy peasy, right? Now they've done the flip. They've given you the data with its like line going through it or its curve, and you're just gonna state if it's a line or a curve. So like, again, super easy. This is a line. What's the second one?
Line.
A line. Tell me. Third one? Curve. And last one, line. No tricks. It's literally that easy, right? So you're gonna see and you're gonna learn to graph these curves. That's what we are working to. So like by the end of this week, I think we could probably start to graph a line. So if I give you data, could you plot this potentially on a graph? So like, okay, I'm gonna think about my axes. These are really big. Do you know where time and distance go? Like which one's the horizontal one and which one's the vertical one?
Time is on the side, distance is on the bottom.
No, time is on the bottom, distance is on the
Opposite.
side.
Time's always on
Mm-hmm.
the top.
Because distance over time.
That's a speed formula, yeah, distance over time. But we usually think as time is like our independent variable, right, Fetty, with our phone in our hands? I'm not blind. I have eyeballs that can see perfectly. And your desks are also empty underneath, so I can see. Time is an independent variable. Time currently is going by, another second just went by, another 2 seconds just went by, and I can't stop it. It's just happening, right? I can't change it. So that's why this one is time. So this like bottom one, or you can think of like the horizontal one, this will be time. And it looks like my maximum time is like 12 seconds. So I can do this in like twos, I think. So I'll say, okay, if this is 0, I'll say this one's 2, 4, 6, 8, 10, 12. Okay, so that worked out nicely, perfectly.
Oh.
Distance is the dependent variable, so the vertical one, because how far you travel is dependent on the time or how long it takes to, in this case, it's just talking about the travel of a Jeep, so a car. So the distance of the car is dependent on how long are you driving for, right? So this is gonna be our distance. Right? And scale is important because obviously I cannot go by ones or even twos. It looks like I should probably go up by like, I'm going to say like 25s. So, okay. So I'm going to do 25, 50. I'm going to go sideways. This is way nicer. Okay, 25, 50, 75, 100, 125, 150, 175, 200. And I have to get to 225, so perfect, 225. Okay, I've got more than enough. So see, half the work is just making the scale, the axes. Now I got a plot. So like these are coordinate points. So like this is a coordinate point, 0, 0. That's gonna be when time is 0 and when distance is 0. So in the corner there. No time has gone by since they're measuring this Jeep driving and it has not traveled any distance. The next coordinate point is 210. So at time 2 seconds, I'm gonna go to 2 seconds, if you can see on here, and I'm gonna go all the way up to 10, which, because our first one's 25, I'm gonna say about 10 is like here-ish. This is about 10, right? A little below halfway point between 25, right? And again, you're gonna estimate. You're gonna do the best that you can. It's a curve of best fit. 420, so that's gonna be right below here. We'll call that 20. And we're gonna keep going. We've got 650. That one I've got a clear point for. So that's 50. And then I've got 100. And then I've got 160. So that's gonna be a little above 150. And then my last point was 12, and that's 225. So this last point. I can't really draw a line for this, because you'll see, if I draw a line from like my starting point to my end point, I'm like missing all of the points.
It has to be a curve.
It's gotta be a curve.
Is the relationship linear or not linear?
What would you think? What's linear?
Line.
A line. So is it a line?
No.
Then it's non-linear, right? So that's all we're calling it. It's not a line, right? So that is non-linear because it's got a curve. Right? See, first page done. Easy peasy. Am I good to flip? Yeah? Huh? Close some windows? Yes. I'll close these two. I don't know if you want to close the window.
No, we're not closing these ones. It's so hot.
That's so hot.
Because you're wearing like so many layers. Okay, so we've been saying, okay, it's linear or it's non-linear. But when we say something's non-linear, friends, when we say something's non-linear, I can give it a specific name because there's a lot of functions that you'll learn, for example, in like grade 11 that are non-linear. But the one non-linear function that you're going to learn this year is the quadratic function or quadratic relation. And it just means it's a relationship between x and y that make this beautiful U-shaped graph called the parabola. Say that, parabola. Parabola, not parabola. Don't say parabola. It's not Ebola, like the virus. It's parabola, right? It's the U-shaped graph, and it looks like a perfect like mirror in the y-axis. And you can tell based off an equation, but also off of a chart, if something's gonna be linear or quadratic. So if it's the first differences are the same, it's gonna be a line. And if the second differences are the same, then it's a quadratic. If you're thinking, what the hell is first and second differences? We're gonna do this. So if you wanna find the differences, it's basically like what are your y values going up by or down by? That's what we're figuring it out. So Fetty, you already see something. So 19 minus 16, like I'm starting from the bottom up. I can see like, or even I'll start from the
They're
top.
all three.
Yeah, if I do one, here, I'll do 4 minus 1. So we always do like the bottom minus the top to see like what was the difference. That looks like 3. Same thing here. 7 minus 4 is 3. 10 minus 7, 3. So Fetty already saw the pattern. 13 minus 10 is 3. And I gotta make sure all of them work. 16 minus 13 is also 3. And 19 minus 16 is 3. So therefore, this is linear. This is a line. What it's going up by is constant. It's going up by the same amount every single time. Whereas if you see this equation, 2x squared minus 1, if I go look at those y differences and I say, okay, 7 minus 17, that's negative 10. But then 1 minus 7 is only negative 6. And then even this one, negative 1 minus 1, that's negative 2. So even the first three are not the same. And you can see 1 minus negative 1, that's going to give me 2. And you'll kind of see, wait a minute, these look like they're mirroring. Because now I'm doing all the positive numbers. Whereas before I had the negative version of these numbers. So see how I have negative 10, negative 6, negative 2, and then all of a sudden it mirrors and now it's going 2, 6, 10. That's kind of like a hint, hint, nudge, nudge of the parabola of like that mirroring effect that you see with the U. When you go to do this same thing with second differences, you'll see 6 minus 10, negative 4, negative 2 minus negative 6.
Isn't it negative 6 minus 10?
It is -6 minus 10.
Negative.
Whoop, there you go. Thank you, Fetty. I was just noticing that from that one. Here we go. So -6 minus -10 is +4. And then same thing, -2 minus -6 is +4. And you can kind of see where this is going. 2 minus -2,
-4. Oh, oops.
+4. Here, this one. I'll throw you this one. 6 minus 2, 4. And 10 minus 6,
4.
4. So therefore, this one is quadratic.
Huh?
So those are your two options. Linear if first differences are the same, or quadratic if second differences are the same.
Do they
So,
always have to be the same? Do they always have to be the same between the two differences?
mhm. So if the first differences are the same, that means it's a line. If not, then if you do the second differences and those are the same, it's a quadratic.
What is first difference and second difference?
Then you're getting into those higher level functions.
Quadratic means curved, and
The parabola.
be a line.
Yep, exactly. So like 4, take a couple minutes, turn to the person beside you, tell me, is A and B linear or is it quadratic? And like show me through the first differences and second differences whether it's gonna produce a curve or a line.
So between these ones, it's 3 minus 1, so 3
Speed it
minus
up, come on.
equals 2. 2, so it's the same, so it's linear. And then for this one, 2 minus 5 equals -3. 1 minus 2 equals -1. 2 minus 1 equals 1. And 5 minus 2 equals 3. So now you have to go to the second differences. So -1 minus -3 equals 2. 1 minus -1 equals 2. 3 minus 1 equals 2. So that was really big, oops. So it's quadratic. And it'll be a curve. Yeah. Thank you.